So we have now a second demonstration problem. This one we'll do in Excel. So the problem says, use the 0.01 significance level to test the hypothesis that people who play wind instruments have greater lung capacity than people in general. The sample consisted of 18 wind musicians who had a mean lung capacity of 71. The average mean for the population was mu equals 59, and sigma equals 19.2, normally distributed. So we begin just like before by parsing the problem. We are, in this case, comparing people with people. So I'm going to write people in both population 1 and population 2, and then we'll distinguish what is different. So we have in population 1, people who play wind instruments. And in population 2, who are we comparing the wind instrument players to? To people in general. What is it we're measuring? Well, I can look up into the problem and see that we're measuring lung capacity. And so that is our dependent variable, or dV. And as far as tails go, we need to check if we're looking for higher lung capacity, lower, or just different. And I see this word greater, which indicates that we're doing a one-tailed high test. And that means that we are going to be looking for a score in the upper end of the distribution. So I'm just going to color that in for us right now so that we don't forget later on what it is we're looking for. And let's see if we can't get this to scroll down a little bit. There we go. There we go. So we're looking for a score in this upper end of the distribution, and we don't yet have an idea of what score we're looking for. So I'm just going to put a little bit there to remind us of what tail we're looking in. Our research hypothesis is that population 1, I'm just going to write pop 1 to save place, will have higher lung capacity than pop 2. And the null hypothesis reads just like it. In fact, I can copy and paste it, and I'll just add the word not in here. And I won't add it there because that wouldn't make sense. I'll put it right here before the word have. All right, so now we have all of our problem parsed and we're ready to get going. So next we're describing the comparison distribution. And so at this stage, I usually go into the problem and get the relevant information out. And so looking in the problem, I can see that for the sample, we can find out the number in the sample, and that's 18. So 18 players, people who are wind instrument, and the mean lung capacity for those individuals was 71. The Z-score is also for the sample, but we're going to calculate that later. So I'm just going to leave it down there on the bottom to remind us. Then we're also told in this problem the information about the population. The mean lung capacity for the population was 59. And we know from the central limit theorem that the mean for the distribution of means will be the same. And I simply wrote that there to help you remember. And the other thing that we're given in the problem is sigma, 19.2. 19.2, and that it's normally distributed. So let's begin to find out what we can write down. We know that our center is mu for the distribution of means, which is 59. And I'm just going to write mu. I'll write it out here so I don't have to search for my signal. And then I'm going to put an m there, equals 59. And we will come back to spread, and we know the shape that we're always going to use. We're going to include that word normal, and I'm also going to indicate that this is a Z distribution and that it is normal. And you can always write the word normal because that is an assumption we're assuming we will always meet in here. Next, we have to take our steps to calculate spread. And we know that since we have n greater than 1, we have to figure out the standard deviation for the distribution of means. And in this class, we always do this in 3 steps. We first figure out variance, which equals standard deviation squared. Then we figure out the variance for the distribution of means, that little subtext M there. And that is always going to be variance divided by n, at least so far. That's what it's always going to be, actually. And then standard deviation for the distribution of means, the very last thing, and what we need for spread, is the square root of the variance for the distribution of means. Now, there are shorter ways to get to this, but doing it this way is going to help you understand what it is you're exactly doing. In a nutshell, you're just taking sigma and dividing by n to compensate for the fact that we're getting a distribution of means, but we're doing it by going up to the variance first. So let's go ahead and calculate from here there we go. Let's go ahead and calculate the variance. It's equal. I start with my equal sign. It appears here in the cell and up in the formula bar. And I just click in the cell with the standard deviation. And I use my caret, and I'm done. Next, I have to divide that by n. So the variance for the distribution of means equals variance. I'll click in that cell, and I'll divide by, and it's got 2 of them there. And now I'll click in the cell with n. 20.48 for the variance for the distribution of means. And our last step, number 3, is just to calculate the sigma for the distribution of means. So equals the square root of varm. So I'll click right in there and enter, and we get 4.52. And so that is what's going to be our spread. I'll write it here in the yellow, sigma, and I'll just put an M there instead of trying to make it small, which is supposed to be. I'm just going to leave it big, and I'm going to write 4.5254. All right, we're done with step 2. That's the hardest step. Next, we look up our cutoff z-score, and we need to know alpha to do that. And up in the problem, it will always state what alpha is. If it ever doesn't state, just use 0.05. But here it says 0.01 significance level. And whenever you see significance level, you're also talking about alpha. They mean the same thing. So we're looking at 0.01. We already established that it's one-tailed high. So what z-score is associated with that? To determine that, we need to simply get out our z distribution calculator. And I inadvertently closed it out, so I'm going to pull it up again real quick here. So here is our calculator tool. And you can see alpha, again, that's the significance level. We change it to 0.01 and we hit calculate. We already determined when we parsed the problem that we're looking for a one-tailed high test, which is the same as a right-tailed test. And critical value just means the cutoff point. And so we are going to write it as Z alpha, Z with a little a next to it. Z alpha is 2.33. So I am going to put that in here. That is our cutoff point. ZA equals 2.33. I didn't have to put a negative sign in front of it because I was looking for a one-tailed high test. Now I can know exactly where to draw the line. I actually went a little far here. We actually have a cutoff point right about here. It would actually be a little further on, but I made too much yellow there by accident. So I'm going to write Z alpha equals 2.33. So if I get any sort of a sample z-score more extreme than that, I can reject the null hypothesis. If my sample z-score falls in this region, we fail to reject the null hypothesis. So let's calculate our z-score. We know that the formula for z-score is always going to be the same. To put it in generic terms, it's always going to be z equals the sample minus the center of the comparison distribution divided by the spread of the comparison distribution. And in this example, when we're working with mean, that means that Z is going to equal the mean, the sample mean, minus the population mean divided by the standard deviation for the distribution of means. Don't forget that little m at the end. That's what we always have to have with a sample bigger than 1. So let's work that formula. I'll just do it. I'll do it up here, I guess, and transcribe it. So let's do the equal sign. Then we have to click in the cell with the mean, which is right here, minus the population mean, which is right here, closing parenthesis, divided by the standard deviation for the distribution of means. Don't accidentally click in the standard deviation. We have to use the standard deviation for the distribution of means. And we get a z-score of 2.65. Z equals 2.65. And in our last step, when we make our decision, we can mark that score onto our chart. Let's get a red out so we can tell. 2.65 is larger than 2.33. It's going to fall right around here. Z equals 2.65. It falls into the region that allows the researcher to reject the null hypothesis, and the researcher will be happy. He likes rejection. His hypothesis was supported. So we're going to just write reject HO. That means reject the null. And I'm going to go up here and actually reject it. If we don't reject it, it stands. So now it's rejected. Right here is our research hypothesis, but we're going to write this all out in understandable words. So I'm going to write, keep coming up with these little boxes that I evidently put in at some point. There. So now let's see. We're going to reject HO, and we're going to say people who play wind instruments. I don't have to write the word will anymore. I can just write have because we've done the test. Have greater. Oh, I forgot a word. We want to always write this word significantly. It's an important word in statistics. Significantly greater lung capacity than, and let's, another one of those boxes. Oh, goodness. Then people in general is what I'm going to write in just a moment after I get rid of yet another box that I seem to have put in there. Then I'll write it down again here, people in general. And then we write our statistic at the end in parentheses. We're doing a z-test, so we start by writing z. And then in subtext, if you're writing by hand, if you're not writing by hand, just write a parenthesis and write the number in the sample. 18 equals, and now we put the z-score for the sample. Don't mistakenly put the cutoff point because we want to know what the sample got. And then we write down our alpha level, but we always put the p first. So a lowercase p indicating the probability of getting a group of people with such high lung capacity if we just drew a chance from the population. Oh, that's what that little p means. All that is less than 0.05 or 5%, period, and then closing parenthesis, period. So that's the appropriate way to write the conclusion. Nickel and dime deductions if you don't do that. Otherwise, this is how you solve that problem. And I hope this was helpful to you.